Reaction rates. Rates of reaction can be determined by monitoring the change in concentration of either reactants or products as a function of time. So you can see the times up here, 0 seconds, 20 seconds, 40 seconds. And here you have 1 mole of this A type of compound, element, whatever. And then it starts turning into B, and those are the blue ones. And then you have some A left and some B. And notice 1/4 of it is A, 3/4 of it is B. So you monitor that change and we can come up with reaction rates. We have a reaction where we have butyl chloride reacting with water, forms butanol and hydrochloric acid. We measure the concentration of the butyl chloride, right here, one of the reactants, at various times. So we have a table of times, and then we have a table of its concentration, the molarity, which is moles per liter of solution, and it's a capital M, see the capital M there. And what do you notice about the C4H9Cl, butyl chloride? There are brackets around it. That just means its concentration. And what do you see here as you go down in time? You start with 0.1000, capital M, molarity, and you go down to where there's none left. It's all reacted. The next step is to find the average rate of reaction over each small time interval. So that's going to be the change in concentration divided by the change in time. So you can see we take the first two here, we subtract 0.0905 from 0.1000, and we get that number. That's our average rate. What do you notice about the average rate as we go? All right, it gets much smaller. And just to make a comparison with physics, it's the same as velocity or speed, if you're more familiar with that, where you have the change in distance or displacement over time. And then if you really want to get fancy, you'll be taking calculus someday, and that's called the first derivative. That's differential calculus. But for here, let's stick with chemistry. The average rate is the concentration of your reactant, which is butyl chloride, over unit time. As we pointed out on the last slide, the average rate decreases as the reaction proceeds. So we had the concentration decreasing. That meant the average rate was decreasing. Well, in this case it did. And that's because as the reaction goes forward, there's fewer collisions between reactant molecules. You have less and less molecules. Now this over here, once again, to make a physics analogy, that's negative acceleration. Acceleration is the change in velocity over time, where this rate, okay, was the change in concentration. So now the fact that the rate is decreasing, that's kind of like a negative acceleration. That rate's decreasing. And if you want to get fancy again, that's a second derivative in calculus. So if nothing else, you've heard these words, so when you do get to calculus someday, hopefully you'll remember it from here. We will now plot the concentration of the butyl chloride on the y-axis versus time. And you can see how it's decreasing, right? That's the green curve. And when we were taking the average rates, we would take the concentrations at 2 points and divide it by a time interval. What if we wanted the reaction rate at a billionth of a second in time? Then there's a mathematical way of doing that. You would take where you want your instantaneous rate, let's say over here, and then you would draw a tangent line to that point. Now a tangent line, let's pull one up, that only touches the curve at one point. Maybe you've had that in math, maybe not, but let's see if I can draw one. Okay, now let's move that. And if he just touches the curve, I can't really get a hold of that line. There, it's touching at one point. We can now find the slope of that line, and that will give us the instantaneous rate at that exact point in time. In calculus, again, that slope is called the derivative. And going back to physics, the slope of the line on a velocity versus time curve would be acceleration. The tangent to the curve of the first derivative of function is called the second derivative in calculus. Okay, so don't worry too much about that, but it's good to expose you to stuff that you're going to see later on. But the key here is to find the instantaneous rate, take the slope of a line tangent to the curve at the point you're interested in. all reactions slow down over time. And the reason is you have less reactants, less collisions, a shorter rate, a smaller rate of reaction. So if we want to find the best indicator of the rate of reaction, we want the instantaneous rate near the beginning of the reaction, up here. At this time, we assume we're looking at the rate of the forward reaction, and we're not worried about what happens if some of the products then go back to the reactants. We'll deal with that later in equilibrium. So 2 points. Find it right here, right in the beginning, and only worry about the forward reaction. Let's bring in stoichiometry. In this reaction, the one we've been dealing with, the ratio of butyl chloride to butanol is 1:1. Why? Because each one of them has a 1 assumed in front of them. 1 mole of the butyl chloride, 1 mole of butanol. Thus, the rate of disappearance of butanol is the same, the rate of disappearance of butyl chloride is the same as the rate of appearance of butanol. And we do a little math here. There's the rate, and here's the concentration of butyl chloride. And notice we have a negative here, right? That means it's going down. And over on the right, we have the rate of the appearance of the butanol. And we have a positive because it's growing. And this symbol here, believe it or not, that's also coming from calculus. That's a partial derivative. But for now, we're just going to worry that it's a small change being measured. And that's getting closer to our whole concept of an instantaneous rate. Small change of concentration over a small period of time.